AI is changing everything, from how businesses make decisions to how machines understand language and images. But here's the truth nobody talks about. AI can't work without data mining. It's the process of digging through raw data to find the patterns that make AI smart. This video course is Introductory Data Mining. The book the material comes from is Data Rookies, Data Mining Basics, available from Data Analytics Curriculum LLC and can be direct downloaded from the website. In addition, there are supplements and lab exercises for download. Chapter 3: Data Preprocessing. Data preprocessing. Essential step to prepare data for mining. Involves data wrangling, cleaning, modifying, restructuring. Data preprocessing is the second of the 5 major steps in data mining. Welcome to Chapter 3, Section 6, Principal Components Analysis, or PCA. In this lesson, we'll learn how PCA helps simplify complex datasets by reducing the number of variables while keeping most of the important information. By the end of this lesson, you'll be able to explain the purpose of PCA and when to use it, interpret a Scree plot to choose the number of components, and understand how principal components summarize the original variables. What is PCA? Principal components analysis is a dimensionality reduction technique. It takes a dataset with many correlated variables and transforms it into a smaller set of new variables called principal components. Each principal component is a combination of the original variables that captures as much variation as possible in the data. In other words, PCA helps us find the main directions or patterns in our dataset, the dimensions along which the data vary the most. You can think of PCA as a way to rotate the axis of your data to find the angles that best summarize the variability. It doesn't delete information, it simply re-expresses it in a more compact form. Example: cheese tasting dataset. Let's take a simple example. Imagine a dataset of 20 cheese samples that were each evaluated on 4 variables: acidity, sulfuric acid, lactic acid, and taste rating. If we look at scatter plots between these variables, we might notice many linear relationships. That means some variables overlap or provide similar information. For instance, acidity and taste might be closely related. This redundancy tells us that the dataset could be simplified, and that's where PCA comes in. Why reduce dimensions? When data has many variables, it becomes harder to analyze and visualize. PCA helps by creating a smaller set of new variables, called principal components, that capture most of the information from the original data. The number of possible components is equal to the number of original variables, 4 in this case. But we usually keep only the first few that explain most of the variation. The goal is to retain as much information as possible while reducing complexity. The Scree plot. A common tool for deciding how many components to keep is the Scree plot. This plot shows how much variance each component explains. Typically, we look for an elbow point, the place where adding more components doesn't add much additional information. In our cheese example, the first 2 components might capture around 85% of the total variance. That means we can use just 2 components instead of 4 and still represent the data almost as well. Principal components as new variables. Each principal component, often labeled PC1, PC2, and so on, is a linear combination of the original variables. That means each variable contributes to each component with a certain weight, sometimes called a loading. For example, one component might be calculated as PC1 equals 0.46 times acetic plus 0.51 times sulfuric plus 0.50 times lactic plus 0.51 times taste. These weights tell us how much each original variable contributes to that component. We interpret the components based on which variables have the strongest weights. Understanding PCA loadings. The loadings help us understand what each principal component represents. If the first component has high weights for acidity and taste, we might interpret it as representing overall flavor strength. The second component might capture something else, perhaps balance or smoothness. It's important to note that PCA works best when the data are normalized first, so that variables measured on different scales contribute fairly. For example, acidity measured in milliliters shouldn't dominate taste ratings measured from 1 to 10. Interpreting PCA results. After performing PCA, we can use the new components instead of all the original variables. For example, instead of analyzing for correlated measures of cheese quality, we might analyze only 2 uncorrelated principal components. This not only simplifies analysis and visualization but also helps in other tasks like clustering or machine learning, where fewer, more informative features can improve performance. Summary. Let's summarize what we learned. PCA reduces the number of variables while keeping most of the information. Principal components are new variables formed as combinations of the original data. Scree plots help us decide how many components to keep. Normalizing the data ensures that all variables contribute equally. Modern software tools like R, Python, or Orange perform PCA automatically, so you don't have to calculate anything by hand, but it's important to understand the concepts behind it. That concludes Lesson 3-6, Principal Components Analysis. In the next, remember, the book and supplemental resources are available online at Data Analytics Curriculum's website.